Good. All right. Thank you. Well, thanks everyone for coming out. I have gone through this journey, and as Pratik mentioned, kind of started here at Penn in many ways, and left Penn to join a startup company. This is the LaneHawk that was mentioned, doing consumer robotics and then loss prevention. But about 10 years ago, almost, joined this company, Blue River Technology, doing agricultural robotics. And so it's just been an exciting journey for me, and I want to focus on kind of the most recent things we've been working on. And I kind of subtitled this thing, Bringing DL to RL, Bringing Deep Learning to Real Life. And that's, I think, one of the key focuses for us is that we're taking these things that are really advanced technologies and bringing them into production. And it's this partnership that I'll talk a bit about with John Deere, where we're seeing these systems, these robotic and deep learning systems going into production and at a large scale. And I'll talk a little bit about some of the scale and hopefully show you through some videos. The way I wanted to just kind of structure this talk was to first give you just a brief introduction of Blue River. Most people probably have never heard of Blue River. We're a small company, but I'll get into the details, that was acquired by John Deere. And then I want to talk about a couple of the products we're releasing right now and just go through some of the technology underlying that, give you a sense of what that looks like and where we're focused, and then talk about a couple of new things that we're working on in the construction and forestry group. So maybe just to start, Blue River, yes. Thank you, yes. Can I? If I can, I will. That good? Thanks for that. Yeah, definitely. So Blue River was founded about 11 years ago by a couple of folks who were in a graduate executive master. That was me, I think. Executive master's program at Stanford. We were acquired by Deere about 5 years ago. We're about 250 people right now, based in Sunnyvale, California, so the Bay Area. We have a 100-acre test site that we use we grow plants, we spray and kill plants. We're better at killing plants than we are growing them, I'll admit. And we also test out new equipment and new ideas there. It's about 45 minutes south of our office, so it's really nice to have this big scale test farm that we can do things with. Our mission is to create intelligent machinery that solves monumental problems for our customers' challenges. Some of the keywords there, intelligent machinery. So this is where the robotics comes in and controls and deep learning. We want to tackle big problems. So Deere solves great technology problems all the time, John Deere, but we want to tackle the big problems that they have a harder time getting at. And the customers is emphasized also because that really drives us. We're very passionate about solving problems that customers have, real problems that will make their lives easier and better. And I should mention, I think most people are generally aware of John Deere. John Deere is the #1 agricultural machine manufacturer in the world. They are just an amazing group to work with and just build these beautiful, solid, rugged products that last 20, 30 years and do incredible things in terms of agriculture and construction. I won't spend much time on this. This is just to give you a sense of Blue River. When we think about kind of smart machines, we do a lot of kind of sensing, decision-making, acting, and then learning also. So we do a lot of calibration, online calibration, validation of our work. So that when you spray something, you want to know, did it work? We've done a lot of work in that area. So it's this very big feedback loop with smart machines and data at its center. Underlying all of this, probably no surprise to folks here, computer vision, robotics, machine learning, deep learning, some of our core strengths and core focuses. But I'd also want to tie in one of the big things that I think it makes us work well is product management. I think that don't think about that as much from an academic perspective, but in business and in developing these products, there's a very strong partnership with product management, who are kind of the voice of the customer, and the engineering side and guiding that. And that's been huge. And I think even if you think about startup companies, it's one aspect that sometimes gets missed, is having really good ties into product management. We also have field testing, agronomy, so a lot of folks that get out in the field and understand the customer. And we try to be very nimble, innovative, and talented. This is the group that we target. Again, just to give you a kind of a rough sense of things I want to talk about today, See & Spray Ultimate is a new product that is about spraying, and I'll go into a lot more depth in these. Autonomous tillage is an actual autonomous tractor doing tillage. And we're getting into construction and forestry. I'll give just some insights into that. All those are also based around this machine learning data platform and also a control center of excellence that we have at Blue River. So machine learning, you'll hear that over again and over again. The kind of the data, the machine learning infrastructure is a huge piece of it. I won't go into that today, but I never want to underemphasize that because it's really core to what we do. So let me just jump into the first project I want to talk about is See & Spray Ultimate. It's a new product that we're releasing. Before I dive into that, though, I want to talk a little bit about why agriculture, what motivates us to work in this area. Obviously, it's the food we eat. That's a pretty easy one. Whether directly or indirectly, the food that we eat comes out of agriculture, and clothes we wear very often. Things like cotton are one of the big farming output products that we work on. And there's also this challenge that as population continues to grow and people move more and more away from rural settings, that we're needing to increase farming production, the productivity of the farms. So studies have predicted, and you see lots of different numbers thrown around, but that we may need to double farm output by the year 2050. But there's huge challenges to that. So things like labor shortages, aging farm population. The top right graph shows some statistics on the aging farm population. People are getting older and older that are working in agriculture. There's also a shift away from working in agriculture and living in rural areas. This bottom right graph shows some interesting trends. The blue lines is the population of farm workers, which shows that it peaked somewhere in roughly the 1920s, 1930s. But as a percentage of the population, it's gone from 70% of the people working on the farms to around, the numbers are hard to get exact, but around 1 to 1.5% of the population working on farms. So you've got this massive drop off on the number of people working on farms. And then the amount of farmland isn't changing. So it's been almost static for the last 20, 30, 40 years. So you don't have this easy way of increasing productivity on the farm. At the same time, we've got these challenges as we continue to scale the farm practices. There are things competing against like weed resistance to herbicides. So the herbicides that are being used to control weeds are becoming less and less effective. I'll talk a little bit more about that. And at the same time, we'd like to implement greener practices, regenerative farming, reduce the use of fertilizer, water, herbicides, all of this. And that's where we come in terms of where our first focus is in that last bullet. So just to give you a sense of what happens today, currently kind of the standard practice is that the way you get rid of weeds is you have genetically modified seeds and you spray the entire field. It's called broadcast spraying. You just take a sprayer like this one and just broadcast everywhere, your herbicide everywhere. So it's just designed to kill all the weeds. The plants are genetically modified to be resistant to the sprays, so they survive, get knocked back a little bit, but seems great. And for 20 or 30 years, that's been a really effective way to control weed populations. And getting rid of weeds is important because it competes with your crops. But what we're seeing is a huge growth in resistant weeds. So through evolution, through sometimes ineffective application of the materials, the weeds are becoming also resistant to the herbicides. So this just kind of walks you through. In 1995, there was a handful of states that had these weed problems. By 2005, it's about half the states. 2015, it's almost every state has these challenges. And so, and the hot spots, especially around the Delta in the southern region in California, show that this is just becoming a huge problem for farmers. So where do we come in? Well, we started with, and I like this history just to kind of show you a little bit of that top picture shows where we started right after the Deere acquisition, we had this 40-foot wide machine that had these huge hoods over them because the computer vision in an unconstrained environment was really challenging. So we wanted to diffuse the light, get rid of harsh shadows, control the wind by giving a little hood. So that's where we started. It was pulled behind a tractor. By the next year, we were demoing something without the hoods to be able to deal with sunlight and shadows and everything. The next year, we were on a sprayer, no hoods again, spraying water and testing it out. And then we're now launching this project. And it was launched earlier this year. It'll actually go into market early spring next year. To give you a sense of the scale, this is a 36-meter wide boom, so roughly 120-foot wide boom. It drives at 20 kilometers per hour, so 12, 15 miles an hour. It's got 36 cameras, one every meter, 10 NVIDIA Jetson Xaviers, so a lot of horsepower on this thing. They all had to be hardened, and that's also been a big project. Rujan was actually asking me earlier about, do we make our hardware? And yes, we buy those chips, but we have to build the hardware that lets it survive in these types of environments. And that's true. Our cameras also, we build those internally. It's got a dual spraying solution, which is kind of cool, but I won't dive into it. It allows you to spray two different applications at the same time. The thing that I really want to emphasize, though, is what we had hypothesized and what we're proving out is we see savings of anywhere from 50 to 80% of the herbicide usage. So we're keeping that from being sprayed on the crops, on the ground, everything.
Great.
How do we control the spray? There are nozzles that are solenoids that turn on and off. Yeah. So we determine when to spray based on vision. It is all computer vision. The amount is controlled through a solenoid that has a little nozzle tip that's a solenoid, just a little actuator that turns it on and off, and then it sprays out of a nozzle. And I have a quick video that maybe you'll be able to see. Yeah.
And this tractor is driven by someone. It is not.
This is not autonomous. That's right. This is driven by someone. This is they call it a self-propelled sprayer. It's a high clearance tractor, effectively, but unlike a tractor, you can't change out the boom. So the boom is fixed and it folds, but it's attached, rigidly attached to the machine. Yeah. That's exactly it. Yep. And we do retrofit onto existing booms, but it's still an attached self-propelled sprayer. So like you buy the entire product. Yeah.
Are you spraying on the go at 20 kilometers per hour?
Yes. Absolutely. Yeah. And they'd like it to be twice that, but actually by law, by regulation, you're not supposed to spray much faster than that because it starts to just kind of get everywhere. Yeah. It does not. Yeah. And I'm not going to talk about that specifically. So it does not. So we have a separate kind of branch that is really focused on the herbicide resistance. Thanks. That's a good call out. That we have a version that is targeted to just spray on the weeds only. And this one does not. This one we're spraying on crops as well. So it uses a selective herbicide in the same way. Yeah, great call out. That's a good point. The key, though, that I do want to focus on is this idea of reducing herbicide usage. And it's massive. We've been just testing on a set of machines that we've built for testing purposes only this year. And we've already, in those trials, been able to measure 3.5 million liters of herbicide that has been kept from being sprayed. So I just can't even imagine what that's going to look like as we start to deploy these machines across. We have agronomists. So I don't know if I could quite call them chemists, but yeah, that deal with the chemistry, understanding of the mixtures, exactly. Yep. And we run a ton of field trials. So that's maybe the other thing that I didn't say, but hopefully implied, is that we're seeing these savings with no change to the efficacy of the control. So we're controlling weeds just like you would if you had sprayed the entire field, but doing it with this massively reduced herbicide. And we haven't yet measured, we expect we'll also see better yields out of the crop, because even though the crops are genetically modified to resist the herbicide, they do get a negative impact. There's a negative impact. You'll see them kind of droop and have some adverse effects, but we won't be spraying mostly on the crop.
The sake of students,
Mhm.
please tell them that it's a truly interdisciplinary.
Oh my goodness, yeah. Yes,
Have a vision that
Yeah.
you learn only one thing.
yes, and I guess I didn't really emphasize it as much. When I think about Blue River, it's about having mechanical engineers, mechatronic engineers, electrical engineers, computer scientists, computer vision, agronomists, again, product management. Yes, 100%. Yeah, and of course, we're just building the computer vision and spraying components of this. John Deere is building this entire machine around it. So there's, yeah, it's a great engineering problem. Yeah. No, you can't just do machine learning, and yeah. Boy. In fact, I feel like most of our time is not necessarily on machine learning. It's a fraction of what we spend our time. This is a pretty quick snippet of video, but I just wanted to give you a sense of kind of what this looks like in practice and the scale. So if you blink, you'll miss it, but I wanted to show a little bit about, we talked about the sprayers, and you're asking about, kind of what the spraying looks like. This is it as the nozzles turn on and off. And then I just wanted to show, this is kind of the scale of the machine. So it's a 120-foot wide boom moving through the field. So that's the size and scale we're talking about. So let me just talk about the tech stack some. Again, this is why we're here. There's obviously not a lot of equations here. I can't kind of publish all of the internals, but I wanted to at least give you a sense of what this is looking like and try and give some insights there. We have this thing we call the see and act pipeline, SNAP. It just was a little bit catchy. See and spray is what we call the product typically. This SNAP pipeline has to run within 120 milliseconds total, glass to glass, we call it. So from, well, actually, it's glass to ground in this case. From the time the light enters the camera into the spray hitting the ground. Yeah, actually, I think that number is spray being controlled and sent. It's another around 70 or 80 milliseconds for the spray to hit the ground. So you can imagine all the compute we have to do is basically order of magnitude the same amount of time that it takes for the spray to reach the ground. So that's kind of the compute that we have. A couple of things I just want to highlight in this. This is just a flow chart of what happens, but we are doing a full boom pose estimation. So in real time, we're measuring through GPS, through IMUs, through pretty poor ultrasonics, the pose of the boom, so that we know how high it is relative to the plants, because that controls timing. We're also doing inference, as I mentioned, on these NVIDIA GPUs. We're mapping out where the plants are, again, in real time, and then controlling for a single compute module, and I mentioned there are 10 of these. They'll control between 24 and 48 nozzles. It's a deep learning architecture. We couldn't do this without deep learning. I'm pretty convinced of that. We tried 7 years ago, probably, to do it with typical traditional like SVNs and things like that, but SVMs. But the performance levels we got out of it just weren't there. Right? And we couldn't get the high performance we needed to be able to detect all the crops, detect all the weeds, and then also segment them from the crops. So a couple things to call out of this. I mean, it's what you'd expect, right? So it's image comes in. We use kind of a pyramid type network that's not overly deep, 19 convolutional layers. I wouldn't say it's a very deep network, but it does run very fast, 8 milliseconds per image. And we have a training data set of over, at this point, it's over 300,000 images that are labeled. And they're all semantically labeled at a pixel level. So big effort there to get that going. And the other thing I want to emphasize on that, I haven't talked as much about data collection. I'll talk a little bit more about it in the next project, but this isn't like 300,000 labels labeled images from like a single field, right? We want diversity here. And so this is images that probably represent over 1,000 fields at least. Actually, well, I can give you a pretty good estimate because we try to capture anywhere from 200 to 500 images per field. So it's probably closer to a couple thousand fields that we've gone over.
Is it specific to a particular kind of crop and a particular type of weed, or is your 150K images?
Yes, so it's a great question. Yeah, we focused on 3 crops primarily so far: corn, soybeans, and cotton. So it's those 3 crops that we've got the bulk of the data is from, and primarily in the United States.
And
so
the weed is just any undesirable plant, like it seems like an open set of.
That's right. It's very broad. Yeah, yeah. And so getting coverage there. This is another thing in terms of diversity of the data that has to get collected. That's right. The funny things too, like if you're in a soybean field and there's a corn plant, that's a weed instead of a crop. And so having to be able to deal with that. And they're called volunteer corn. I always love the name. So but they've kind of volunteered to grow up in the field, left over from the previous year or something. Yep. And so that's another big area of focus for us is how do you transition to new crops, new weeds, new geography, all of that. We spend a lot of time there.
How much pre-processing is done before you run the deep network?
Pre-processing of the image? Very little. Maybe I'm misunderstanding. No, we don't do anything. Yeah, I see what you mean. No, it's the images are basically passed in. I mean, there's a lot of pre-processing in terms of lighting adjustments, tone mapping. We do a ton of augmentation. There's a bunch of things that go on there, but nothing really to the images besides just some basic image processing. But no extraction, no feature extraction. We also built visualization tools. This is just to show kind of each image probably only covers a couple meter by a couple meter area, but what you can see here is probably a 20 or 30 meter by 20 or 30 meter snapshot of what the robot is seeing or what this machine is seeing. You can kind of get a sense of the little tick marks along the way on the pink and purple lines. Those are actually just images that have been stacked on top of each other and just they're off enough that you can see the difference. So you can see probably a couple hundred images going across there, but as you start to pull together what they're seeing, they're all stitched together to make sense. Another thing that has been really interesting is we figured, hey, we've got this deep learning network. What can we do with it? So call it multitask learning, but that's probably a glorified way of saying we're just going to pull a couple other things out of it. In this case, in addition to having our encoder that kind of extracts and consolidates the data, we'll pull out whether there's too much dust in the image or too much blur in the image or too low light. And so have it detect image quality issues at the same time as it's extracting where the weeds are and where the crops are. And that's just nice because we've got the data, we've got this machine learning model that's built, that's already doing all this work. So let's just leverage right on top of that. And I keep mentioning data. The one thing I love about where this work goes is that data continues to make this product better. And not just this product, but other products. So if you think about, we're doing spraying today, and we can leverage kind of data capture across a whole fleet of machines to get better and better and look for where there are problems. And we can also then start to use these machines will go into the same field multiple times. So we can start to measure our performance, the first application versus second application, see how we did and get feedback that way. But Deere also has this whole fleet of machines doing other things. So planting, tillage, harvesting, fertilizing. So you've got this ability now to measure across an entire chain of the agriculture production process to see how is each step impacting the next and pull that all together all the way through harvest and do that again on a large fleet of machines. So the data, the ways in which you can use data, and we're starting to really expand on kind of the data science aspects of what we do. It's just enormous, great potential. Okay, so that was See and Spray. Let me switch gears to talk about this autonomous machine and autonomous tillage. Yeah.
So the data that you mentioned, am I right in assuming that it haven't open sourced it?
No, we have not. Yeah, I do get that question a lot. I've had that fight a lot internally. I would like to. No. I mean, that's the simple answer is no. And I think, yeah, it's been a challenge. I think we're continuing to look for opportunities of how we might do that. It's as you can imagine, maybe this is a little bit implicit, but I'll say it explicitly, it's this balance between having this data as a distinguishing factor in our systems versus wanting to get it out to the community and share it. And so I would like to, but we have not yet. Yeah.
So you have all this like really rich video stream coming from all your cameras on these vehicles.
Yep.
And of course, you're looking very specifically for the weeds and how to spray them. But
That's right.
you could be using all of this data for monitoring other things like how's my crop growing? Is there
Yes.
disease on-
Yes, exactly. Yeah. And you know, when I show something like this, that's exactly the way I'm hoping you think, or that's how I'm thinking for sure. Yeah.
How integrated with your, or is this more like you have this platform and then you try to add something on top of it?
No, it's fully integrated with Deere. I'd say we're still trying to figure out exactly how to integrate it into the broader Deere ecosystem that includes the data analysis. You know, we've kind of focused on the data, but I think getting Deere access to all of this data is something we're working on. But yeah, no, it's Deere teams working side by side with Blue River folks, integrating into their systems, into their displays. These maps, kind of the maps that I was showing, get displayed to an operator through the Deere, all the Deere. Yes, exactly. Yeah. So it's, and I was mentioning it's called See and Spray Ultimate. It's going to be sold on all Deere machines going forward, starting this next spring. And hopefully existing Deere fleets also in other regions. Yeah. Okay. All right. So again, let me jump over to autonomous tillage. So I think this is also a really interesting area. In tillage, and maybe again, stepping back, sorry, sometimes I forget that I'm so immersed in this. Tillage, this is an operation. Generally, it's pulled behind a tractor, and instead of the single machine, it's got a tractor that pulls what's called an implement, usually some type of plow, in this case, a chisel plow, that goes through and tills the field. So it usually has some operations that help clear brush out, and then maybe turns the soil and gets it prepared for planting for the next season. We've chosen to start in tillage, and I think this is just interesting. And you know, as if people are thinking about a product and how to approach product management and product marketing, this product is interesting to choose tillage because it's this valuable operation for autonomy. Because it's this valuable operation that farmers need to do, but it happens roughly at the same time as harvest. And so if you think about labor shortages and the challenges farmers face around labor, if they've got to choose between harvest and tillage, they're going to do the harvest every time, right? I mean, you've got to harvest your crops. And so tillage is very often this thing that either gets lost or missed, but the farmers want to have, or they put their least skilled labor there if they can find it. It's also just a simpler problem around automation and autonomy. There's not plants in the field generally. If you mess it up, you just go back and do it again. You can't do that with harvesting or planting. If you mess those up, that's your last chance. You don't get to go back and do it again. And then we'll expand from there. I kind of mentioned this earlier, but well, it was announced at CES this January, but we're launching it and it'll be available as a product on Deere machines. Again, this is all through Deere this next spring for model year 23. And these are just some pictures to show you kind of what it looks like running. I'll show a video in a second. I love this one on the bottom right, which is how it operates at night, because they operate very often at night. So you can see the lighting patterns that go on there. And then I mentioned data collection, and I thought this was kind of a fun picture to show. These are some of our data collection rigs where we've retrofitted a gator, which is just a kind of a golf cart type vehicle to be able to collect data. And what's interesting about this is they need to be able to compress down for shipping, but then they kind of transform out to have the cameras and the lights and everything placed where a tractor would have them. So these vehicles all have this, we kind of nickname them transformers, where they can extend out and go out and collect data. And that allows us to get into lots of different fields, lots of different situations very quickly, rather than trying to bring a tractor to every field. And we've done this to collect data with See and Spray, even with just backpacks, people wearing backpacks walking through the field. But that's been a big effort of ours, is to be able to collect data quickly in a diversity of geographic locations. And I just wanted to show some of the results of computer vision, machine learning. These are, again, deep learning networks. These probably won't surprise anyone. The left column is images. The second column is the ground truth, the labeled data. The third column is the results out of our neural network. The fourth and fifth columns are actually, this is an experiment around depth. So the fourth column is depth measured from stereo. You see there's a lot of noise there. And then the fifth column is if we feed in depth to our machine learning model and clean it up. And this one doesn't look even as good as it typically is. So we've got much better depth from stereo and through a machine learning model in kind of our more recent work. So yeah.
How do you supervise that model?
Yeah, so the original versions were actually supervised by the stereo depth. But what we've done is now we use unsupervised methods that use the disparity, kind of the estimated disparity between the stereo pair to train and train the depth model. So it's an unsupervised method.
And does the autonomy, especially at night, also rely on vision-based?
Yep. Yep. So night also is all vision-based. In fact, what's interesting, night in some ways is easier. It surprised me when we first got into it, but night you have good solid illumination that's consistent every time. And so there are a number of things about working at night that are easier than the daytime for doing computer vision activities. As long as you've got enough light, so you can't see what you can't see, obviously. But and so this is just showing kind of how the system performs on the night model. And yeah, like I said, the performance is actually in general better. There's a couple exceptions to that. One that still makes me laugh is bugs. So bugs come flying by and they get lit up by the camera and they look like an obstacle. And so dealing with that has been an interesting one. And then dust. Glare that you get from dust can be a real challenge at night. And so we've done a number of things to kind of work on that and improve it. And then we talk about integration with Deere. So this is integrating with Deere planning. The Deere machines actually have been driving themselves for 20 years. There's AutoTrack, which Deere sells, which just follows GPS guidelines and will just go and track through a field, but they can't do it autonomously in terms of obstacle detection and being able to stop when necessary. So there's always been a driver there, but the driver doesn't have to do much. But we're leveraging that and leveraging the data analytics, the digital tools. This is just a map showing a field that's been run through the Deere system. So fully integrated with John Deere. And then just to show a couple of videos of what this looks like as it's running. It's actually kind of dull, and that's always kind of the funny thing about autonomous systems, especially in farms. It looks just like a regular system, but there's just not a person in the cab, right? You just can't tell the difference. So that's it running, and here's it running at night. You can see kind of how dust can be an issue there. Just one thing, and so dealing with that, figuring out how to do the lighting properly has been an interesting challenge, and we've incorporated a number of things to help reduce the dust, but also just understanding how to handle exceptions that get thrown when those happen. Start there.
Consumers feel about the autonomy there, especially because the machine learning has a reputation of not being understandable. You're not in the weeds with that technology, y'all worked on, or are there, I'm sure you have plans and thoughts about this, but I'm curious what you've done to develop trust that they would want this technology, despite the fact that they may.
Yeah, it's a good point. We haven't really encountered as much of that distrust or kind of this feeling of, hey, it's not explainable, so how can I trust it? We haven't encountered that as much with farmers. I think generally, especially being in the tech industry, you see that a lot. The farmers, they're much more kind of the show me mentality of like, you show me this working. And I think some of it also has to do with the fact that they're desperate for labor help. Let me put that. So, the farmers have as I mentioned earlier, real challenges with finding labor. And so this idea that they could get something where they can drive the machine to the field, let it run. It's meant to be a closed field. They're not meant to be people around. I think it doesn't have the same issues as maybe an autonomous driving where you're dealing with whatever could happen from anybody else. There shouldn't be anything there. And then they have a really nice integration on their phone, on a tablet if they want, but that allows them to see exactly what's going on. They get the alerts if something causes it to stop. So building that trust, I mean, absolutely, you have to build this trust with them, but it's a lot just about demonstrating the technology working and them seeing it, and then we'll demonstrate, that it can stop for any type of item in the field. And so.
That John Deere pushes its technology and has been for as long as it's been around, been known for its high quality products that push Blue River to seek the same level of excellence in the product level when you're pushing out with the same confidence that John Deere does, the tractor's gonna go?
It's a really good question because that is where we spend a lot of our time, is trying to kind of a meeting of the minds between Blue River and John Deere, I think. Yes, I think it's not one way or the other. I think we're both kind of meeting in the middle, if you will. Because these machines, yes, they have to have the same quality levels that a John Deere machine has. So we don't compromise on quality or safety. But what I think is how do you define that in these situations? And so we will focus on safety and you be able to trade off with productivity. And so you can have this machine stop as long as you can fix it and keep it and going. And so that's kind of where we've focused, is this machine will be safe, but it will be focused on stopping, being able to resolve that problem, maybe even without the farmer's involvement, and then continuing on. And so it's how do you trade that off to make it the reliable product that you want, but also work for the farmer and work for Deere. Sorry, yeah.
Something along the same line.
Okay, yeah. All right. And then this was kind of indicated or got at a little bit earlier, but we'd like to extend the autonomy to the different machine operations that happen in the field. So we've focused on the first one, which is preparing the soil, this idea of tillage, but planting, fertilizing, spraying, and then potentially harvesting. Harvesting is hard. So for autonomy, and unless someone can see through crops and see people through crops, I don't know what it's going to take to do that. I honestly just, I think we'll get there at some point. Obviously, people run through fields all the time, and they harvest crops. But I think these other ones are all ones where the crops are either very small or you can see through as much as you need. So if anyone's got a solution for that, please hit me up. Some type of radar. Yeah.
So harvesting is hard because you do it in phases, or
No.
what prevents you from stopping everything and then doing it separately?
It's just the issue of how do you get the machine through there to chop everything down? So harvesting is one pass for almost all these, especially row crops. You go through and you're chopping it down. You're actually, if you've ever seen a combine or a harvester, they're amazing machines. They call them a factory on wheels. It goes through, it collects all the material. It will strip the corn of all the kernels, collect it, filter it, store it, and then chop up all the waste and distribute that back on the field. And this is all one machine doing this. But it's mostly the fact that you've got, 6, 7, 8 feet tall crops that are standing there blocking your view as you're going through at 10, 12, 15 miles an hour. Well, Yes, I think so. And maybe this goes back to the question, like, we want to be able to see if there's anything in front of a person in particular, but even rocks and vehicles and random things that get left in the way. But people are our main focus.
So I guess the point is that because the harvesters themselves are already on, at least for certain types of crops.
Mhm.
I guess it's the towing of the harvester.
No, it's make. So yeah, it's purely just today, and today the drivers have to deal with being able to see things and figure it out. And I don't know how they do it sometimes, but they do, and they make that operation work. But how could you remove that operator? Yeah, that's the question. Harvest also is the most valuable operation they have, so that's where they put the farmers themselves, or the most skilled labor they have goes into that seat. So it's probably also the one you're least likely to replace with autonomy. Yeah.
Have you tried putting blue cameras up above?
Yeah, we've looked at different things you could do like that. I can't say, we've looked at drones also that can be tethered and fly out in front of you. It's still hard to see through the crop. The crops, it's canopy over, and you just get this dense canopy that is really hard to see into. So yeah.
So it's more challenge on the autonomous navigation side.
Less on navigation. The navigation is fine because you use GPS and that is no problem. But it's more the autonomy, being able to detect obstacles in front of you.
I see.
Yeah.
And
With enough time to stop, obviously.
yeah, and also I guess picking up those things is also a manipulation problem.
The manipulation has been solved, so the harvesters can do that. Yeah, that's no problem. Yeah.
Have you tried sampling modalities with the canopy provider? It's like some of the LiDAR sensors you get.
Right. Yes, yeah, that's right. So we've looked at LiDAR and radar for those types of things, and again, well, yeah, there's new versions of radar kind of that give you a more dense understanding. But you're right, LiDAR can give you multiple returns, or at least returns that that can see further through things.
What LiDAR?
We've looked at a bunch. I mean, we've looked at Velodyne, we've looked at Ouster, but I would say that's not been our focus. So I don't want to claim that, oh yeah, we've solved that problem.
Yeah, a lot of commercial LiDAR. They're a little,
Yeah.
like some of the solid state LiDAR that's being used in AV space. That's
Mhm.
much better.
Yeah. So it could be that, maybe we should talk about it too. Yeah.
Can you speak a little bit about what are these obstacles that you need to avoid? It's really kind of surprising to me that the hard part of harvesting is actually just obstacle avoidance.
Well, sorry, let me make sure it's clear. The hard part of taking the driver out of the harvester is obstacle avoidance. Yes.
Yeah.
There's also the adjustments you need to make that the operator will do. So you have a bunch of things that can be adjusted to deal with crops that have fallen over, or areas where you can go faster if the crops aren't as dense. But for us, it's people, and be very explicit.
Ask people to stay away from the field.
Yeah, the scenario we have that is kind of our number one kind of guiding scenario is someone, I'll say it, got drunk, fell asleep in the field, is in camouflage. And so they're laying down in a field in camouflage, and you're driving through that field. Yeah, that's kind of
These accidents do not happen when a human driver is at the wheel.
Right. Right. Hopefully, yeah. Finding data on accidents in agriculture is really hard. So, but that's the idea. Okay, now I want to switch gears completely and talk about this is not something going to market. This is one that I need probably a whole series of disclaimers to say, please don't do this at home. Don't try this. This is not something we're marketing, but it's fun. So I figured I'd share it. But this is what we call a balancing skid steer. It's one of the things we've been looking at in construction. It's a control project, so it's kind of fun that way. We've taken two approaches to this, and I want to just kind of run through both and compare and contrast a little bit. We've taken a deep reinforcement learning approach, as well as a model predictive control approach. So there's kind of these two approaches, again, just to explore the space a little bit. I probably should have showed the video first, I'm realizing, but anyway, I'll get to that. I want to just kind of give you a breakdown of what we've worked on here. We're using neural networks in two ways in this system. One is to help us simulate the system and just take something that's very nonlinear and help in the simulation. So we've done more physics-based modeling to get you kind of a primary model and base model, and then built a neural network effectively around that, especially around the controls and how the controls translate into some of the action on the machine, to build a better simulator. And then taken that to train a controller, again, this reinforcement learning based controller that can control the machine and then do the sim to real transfer. So transfer that out to the machine. I've been really struck by how effective that's been. Once you get a good simulator, the controller transfers really well out to the machine. And I'll talk a lot about that in just a minute. We obviously had to modify the machine slightly. This is it's called a skid steer loader. It's a compact, like if you think Bobcat, if anyone's familiar with those, but this is John Deere skid steer loader. We added a wheelie bar so that as this thing tips back and does a wheelie, it doesn't fall over. So it gives us a little safety on that side. And then replace the front bucket with a set of wheels also. We also added IMU and GPS and a remote control kit so that we can control this thing remotely. I mentioned we do kind of a physics-based model. What's kind of fun is finding the inertial parameters on the skid steer. So we had to kind of balance it up, put it on a pressure plate to find center of mass and some of the inertial parameters. And then we built it into a simulator, just a physics-based simulator. We use RACIM in this case because we're working with ETH Zurich. And I should say this is work done. Lee Redden, who's one of the co-founders, and Marco Hutter out of ETH Zurich was working on this also. So it was a collaboration with those guys. We then collected data around the actuator control and focused on the nonlinear areas that happen when you try and drive this machine between what you command and what actually happens on the machine. So we ran it through essentially a series of it, like a sweep of inputs to be able to kind of test out the input to wheel speed, wheel velocity, wheel speed state, and then built a neural network that could simulate that. So that was kind of the nonlinear area we wanted to get out. And then had to put also a controller around the simulator to be able to properly have the simulator take wheel speed as a control input and drive the simulation properly that would model that. And this isn't a very exciting graph, partly because the simulator sits on top of the measurement. But the blue lines are the control signals coming in. The green lines are the measured action, and then underneath it is a set of orange lines that are what the simulator said. And so you can see they kind of sit right on top of each other in most cases. So that was nice. I don't probably want to spend too much time on this, but basically just say we kind of use this reinforcement learning setup. Using PPO, proximal policy optimization, with the simulated environment. Over each episode, we'd randomize some of the variables to give it some robustness and add noise and things like that. Again, just some of the details on kind of how we train this model. Building up from having it control the system to balance itself, to putting penalties on motion and control effort and how much the control effort changed. So pretty straightforward in some ways, but obviously a challenge to get that to work. So then tying this all together, again, we have this controller that is able to control the system. Maybe one note is that the controller doesn't work from sitting on the ground all the way to swung up. So we had different policies that we trained for each of those states, both going from the getting the machine upright and also how to land it softly so it didn't destroy itself on the way down. Those are effectively handled automatically by the system, but they're different controllers. Okay, and then just to show you what this looks like. let's see. So on the right, I'm going to start this one up. This one's kind of fun, but it's a longer video. We had it be able to trace out on the field this word hello. So it's going to run for a while, and there's I wanted to show you kind of how this thing pops up and gets into place. So that's one control policy. And then it'll drive around and maybe, because that one's a little dark, I'll show this one. That will do basically the same thing. And it just kind of pops itself up. Again, do not try this at home. There are no operators in the cab, and yeah, it's very important.
Jim,
Mhm.
since you are watching this.
Yeah.
But I don't know whether you were still here 20 or plus
Mhm.
years ago.
Yeah.
Prama Sina,
No, not
he did tactile force sensing on feet
okay.
of how to control rugged surfaces.
Mhm.
It occurred to me that, this would be quite applicable for having some sensors have evolved and improved to put on your vehicles so that you can adjust to
Yeah, different terrains. Yeah.
have rugged surfaces.
Yeah. That would be interesting. The one thing I've been struck by, though, is how brutal these environments are.
Yes,
It's crazy how rugged these things have to be.
Yeah.
Okay, yeah, okay. And then the center video I just put up just to mention is showing some robustness to the terrain. So it's able to go over bumps and changes in terrain that it hasn't been trained to do. It has no forewarning of. It just is able to deal with it robustly. Yeah.
Do you know how hard it is for a human operator to learn to do it?
I've seen YouTube video of
Yeah.
someone doing it. Again, I don't advise it, but I think it's very challenging. Yeah. Again, I've seen one YouTube video, and my memory was that the guy was labeled as kind of crazy, like the guy who would do crazy. Oh, really? Yeah. Yeah. I've never seen anyone do it, obviously, but yeah. And then maybe this last bullet on the page, I do want to just emphasize is that the transfer from the simulation for the controller to the real machine had no retuning. So it just transferred over. It's really pleasing to see that happen. Okay. And then I'll go through this pretty quickly because I know we're probably running out of time, but model predictive control approach, again, is another approach we've taken. This requires a more thorough dynamics model to be able to build out for the MPC. And so we did quite a bit of modeling for that. Built the controller, which has a standard kind of optimization cost function that does this on a fixed horizon, and is able to basically build this controller for the same type of situation. And just to show again some quick videos, they'll look very similar. This one starts in kind of a slightly different position, but the idea is it's able to pivot up, control it, and you can do things like spin it, translate it. The second video shows this whole the machine tracing out the diagram below, and you can see how that runs. Yeah, so very dynamic system. I think I'll keep moving on with that. Just to talk about some of the learnings from dealing with these types of systems and these two different types of controllers. Maybe to start with, MPC is great for dealing with balancing the system. Was much more challenging when the dynamics change. So having those dynamic constraint transitions proved to be a real challenge, and we weren't able to solve that, to be frank. Not that it couldn't be solved, we just weren't able to get there. The reinforcement learning controls weren't as smooth as the MPC, and it could be just how we approached it. We added some first order filtering that got it much better, but just out of the box, it had that issue. The reinforcement learning was great for transitioning to slightly different tasks, but related. So if you had kind of the same model, but you wanted to control the bucket height or do something that was related, it was really nice for transitioning that. Where MPC one in some ways is if you needed to add real hard constraints, kind of limits that you wanted to enforce, that's much easier to do with MPC than it is with the RL. Just some comparisons there. And then I just want to, that's kind of those projects I wanted to mention, just looking forward. We've got a number of things, again, in construction and forestry, adding more and more safety to construction and forestry, but to construction. Construction sites are really challenging. There's a lot going on. And the technology just isn't there. It's funny. We've had operators who say, I feel much safer driving my pickup truck to work than I do in the construction machinery that is there. And it shouldn't be that way. And so Deere's working to improve that. For us, I put this Venn diagram together. I think, the problems that interest us kind of are this intersection between sustainability, scale, and advanced technology. And I think where we hit on those three is where we're most successful. This one I wanted to show. One of the things that we're really interested in right now is in forestry and how can we help reduce or prevent forest fires. Forest fire management is extremely challenging, especially in the west parts of the US where we are. It's a huge issue, forest fires kind of popping up all around Northern California. I want to show this. This machine is an amazing machine. It's called this one's a feller buncher that is able to grab the tree, cut it, and then cut to length the logs that can be then later harvested. But what I want to call out here is I don't know if this will relate for most people, but I have visions of the Lorax here, and I'm a little bit uncomfortable at times looking at this. But forest management, when you do it right, allows the trees to be healthier, allows them to be more resistant to fire. So we think about forest management more around thinning than clear-cut logging. So it's about thinning the forest so that the trees that stay there are healthier. And when you do it right, one of the things that's really interesting to call out, you'll see that they'll kind of take the last bit of the tree, the top, and just drop it in place, and they drive over that, and it protects the ground soil underneath, and it compacts the material and starts the regenerative process for that, so it leaves the material in place. So finding good ways to help automate this. Again, labor shortages drive a lot of the challenges with being able to do enough thinning to prevent forest fires. So being able to manage some of the things that go on in forestry. That's really, really exciting, I think, to be able, if we can do that right. And also finding machines that have lower impact, lower footprint on the environment. And that's it. Picture of the team, because it's a great team. This is us down in our farm in Gilroy, and just fun to work with. Yeah. Anyway, thanks so much. Oh, you know what? And I'll just let this run in the background. I thought since I'm here, I should show when I was here, we had the RoboCup team, the U penalizers, which I know still goes, not legged locomotion. But this is us playing in one of our first competitions, I think in 1997, against a team from France. So I thought I'd just play this and let it run. It looks awful in some ways. I kind of cringe a little bit, but it was amazing technology in the day. So, it shows you how much things can advance.
I think they're in the display case.
Are they?
Yeah.
Oh, awesome. Great. Yeah, go ahead. I'm just going to let that run.
Thank you. So, and does the are there questions from the in-person attendees? And then if not, okay.
For the RL component, right? How much real world data did you need to collect to make that happen?
Not much. Yeah. It was surprisingly limited. It was done in roughly a day. I mean, a day's worth of data collection. There were various things we had to change and tune when we realized maybe we didn't have the right sensor or the right location, but very little data to get that model going. And then obviously once you get your model good, the training is all offline.
For training that model, did you have to have some manual operator performing those kinds of?
Yeah, so interestingly enough, we didn't. Yeah, we were able to do all of the things we needed to train the model effectively on the ground. We balanced it up also and did some work with it static. But yeah, we didn't have to have it driven around inverted or balanced like that. Yeah, it's good. And I don't know if anybody remembers Avik Das. He was the cameraman on that one. He was a GRASP student also.
So you talk about the forestry construction doing and forest.
Yes.
Are you looking at any other applications in forestry as well, or is it like just right now, just that?
Yeah, I think the way I think of it is,
Timber volume estimation.
what kind of estimation?
Timber volume estimation.
Volume estimation. Yeah. No, I think that all kind of pulls together. And I think as soon as you automate some of these pieces, understanding tree species, understanding tree sizes, being able to kind of do planning where you optimize the routes to pick up the trees and distribute them. They all fall into place with that same set of work. But I think you also get into situations like, how do you harvest on a 30-degree slope? And, some kind of really interesting dynamics challenges as well. But even just, to take a step back, just picking and placing and grabbing, the manipulation that has to happen there. That's a great challenge.
You said that data collection is like, very geography specific, crop specific, application specific. So you're focusing on like a few crops, say in the US. Is John Deere or like Blue River Technology considering, partnering with, other companies in different countries so that you can collect data so that over the years you can scale, because data collection can't happen overnight.
Right.
So are you guys considering like, trying to partner with other people outside?
Yeah, I think John Deere scale means that we probably wouldn't end up partnering with other groups. John Deere's a global company, and we're looking to put these systems on John Deere platforms. So wherever they are, that's where we want to be. But that does mean global, and so it means Europe, it means Asia, it means Australia, it means South America, even machines in Africa. So moving into those regions is definitely key to what we have to do. Yeah. So there's no plans to limit it to one particular region. But I think maybe to address your point, we've got the resources and regions, I don't want to say covered, but we've got facilities in a lot of these places so we can get people there and get machines there.
Yeah, so you briefly mentioned drones at the beginning of your talk, but for seed and spray technology, have you tried applying the same camera sensor in the same model just to like a really low flying drone to try and just, I don't know, cut the cost of having a massive boom? And I was wondering why you decided to go with something that fits on tractors.
Yeah, it's a great question. So we haven't ourselves done it, but we've partnered with a third party that's done that. And it looks like this, and you can tell me if maybe it doesn't fit with the model you're thinking of, but you fly a drone, right? You capture all the data of where all the weeds are, and then you run a machine through that sprays it, right? So you're going to run that machine through anyway. So why not just have the camera on the machine as you're going through? And so that's kind of where we ended up. You can do it. It's certainly doable, but it's one more operation the farmer has to do. It's one more complexity that gets tied in. And so at least where we've ended up is put the cameras right on the machine, do the data collection. The cost trade-off, that's I think at the core of where the balance happens. But so far, the cost we can bring down quite a bit relative to the cost of additional operations and having that machine that is just able and ready to go. I don't know if that quite answers the question, but yeah.
Following a bit on that, acknowledging all the difficulties on the field that a machine on the field has to deal with, plus all the complex of operating the machinery, comparing a tractor on a field that most of the time doesn't have humans. There's not so much of a moral element, and for the most part, you can predict what's going on or see, compared to the streets.
Yes.
It seems that the autonomy on the streets, which is, I would say, far more complex, is a lot of kind of years, it feels to me, ahead of where the autonomy on the field is. Why do you think that is? Is it like people graduating from Penn and going to Tesla instead of going to Blue River? Why do you think that is until today? And the first autonomous tractor coming out this fall from John Deere, for example?
Yeah, it's a great question, because for us, it's in some ways so obvious. It's like, if you want to get, and sometimes it's our pitch when we're trying to hire people out of Google or, Waymo, or, whatever, pick your autonomous vehicle company, is to say, hey, you want to actually work on something that's going to be used by people in the next 2 years, 3 years. It's not going to be an autonomous vehicle. And that's starting to change, obviously, that will change. But it is surprising that it hasn't happened before. And I think it's a combination of a lot of different things, but I think John Deere traditionally has been, they call it, an iron company. They build big iron, these big machines that are reliable, they'll last forever, they are robust. And the computer vision side, the things that you need to do like autonomy with, haven't been a core focus. And that's been changing over the last probably 5 or 10 years easily. I think some of it's the technology wasn't ready. So, to your point, autonomous vehicle companies have only been going for 5 or 10 years. So John Deere is maybe playing a little bit of catch up, but is there now. And that's our focus, is to start trying to draw those people in. And it's not always easy to convince someone to go join an agricultural company when you've got all the press and the hype around autonomous vehicles on roads. But when you look at both the constraints you can put on the system, the technology that is there, some of the costs, the margins are different also. You've got much bigger equipment. So I don't know, it just makes so much sense to me that this is where the action is going to happen, certainly in the next few years. And I don't know if it answered your question, but I certainly understand where it's coming from, and I agree. It seems like a no-brainer. Yeah. So that's why I'm here, convince everybody to come over and start working on agriculture and things. Yeah.
Hello, thank you so much for presenting today. I want to ask, to what extent does Blue River plan to develop agricultural technology meant to address resilience to climate-based agriculture effects, for instance, drought resilience, or as you see, like crop failures due to heat waves? Or is this outside the scope, perhaps, of current agricultural robotics and intelligence at the moment? Yeah, it's a great question. I think we're trying to solve. It's this interesting combination of the problems that we can solve with the technologies we have, and the problems that matter. And I think we focused a lot on reducing inputs to the system. We're not geneticists, so we're not going to be improving crops to be more resilient. But we are running these machines through the field, and someone asked this earlier, like, you've got these sensors, what else could you do with them? And so can you detect drought stress, water stress, nitrogen deficiencies as you're driving through the field, so that you go back and add these inputs later. So I think those are the types of things we'll start to work on, and is seeing both how can you adapt to crop issues and pests also. So bugs that come into the field is another one, different pests. But then also, how can you reduce the inputs that you use? And I'd love to reduce fertilizer. We'd love to reduce water usage is another maybe example that would be great to do, but we don't have a good way of doing that. People don't water in that way. And so finding a way to be able to address water usage is really challenging for us. You can't drive a big sprayer with water only through the field to water your plants.
That's all right. Can I ask a follow-up question?
Sure.
Fertilizer?
Yeah. Yeah. So you're asking, have we developed technology that would utilize less fertilizer? So we've been working on that. It's not a simple answer, so I can't say yes, we've got this technology. We've been working on developing things like that. There are lots of things that need to happen, and one of the challenges is understanding what's happening in the soil. So being able to take measurements there, and then being able to analyze, plants and their reactions, and being able to control the fertilizer application. So we don't have solutions for that today, but that's certainly interesting.
Sorry about that. So we're gonna have to put a hold on questions from the audience, so we can take some questions from Zoom, and maybe we can get back to you in a bit. Yeah.
Yeah, so I'm doing the first question is from Tom Zhang. Crop yield seems to have many co-founding factors. Are there good simulators for simulating the crop life cycles?
There are good models. I'm trying to remember if it's University of Illinois, I think has a really good crop model that takes into account things like environmental effects. They have growth models basically for that. So there are simulators for that. We haven't explored that area fully, but yeah, there's some good work out there.
So the second question is that I imagine the cameras can get dirty during the field operations. How do you protect them? Is there an active cleaning system?
Yeah, so we've debated that, thought about that in lots of different ways. What we've seen so far is the cameras have a nice hydrophobic lens coating on them. They're also pretty resistant to dust accumulation. They get dirty. Obviously, that's not something you can't completely get away from. We have some of our monitoring that allows us to detect if there is significant dirt on the lens, and then we instruct the operator to clean it. But so far, we haven't needed a regular cleaning schedule, although we recommend it, but are able to detect when the problems arise.
Yeah, I guess the last two questions are related to the Beasley side. So Tom asked again, how much cost reduction taking into account the cost for additional hardware that you're introducing?
I can't really talk about costs. So both because I don't really know the answer, but also I shouldn't. So it's kind of convenient for me. But there is a significant reduction. I mean, the idea that you're saving more than half of the inputs in herbicide that you would spend on offsets any cost increases from hardware.
Yeah, the last question is from Andrew. So today, humans make decisions primarily based on visual and sound feedback too. If an AI is as safe and is acceptable in ag, or is a practical, is a practical threshold higher, like in car automation? If so, how much is the industry losing by setting such a high bar, and how long will it take to reach the bar?
Right. It's a little tricky to be able to talk to that. We want to make these systems safe. So our goal is to have, to reduce any types of fatalities, injuries, accidents. There aren't great statistics on that. It's not tracked in the same way that you have on vehicles. So we don't have great numbers on that, but we're going to do whatever we can to minimize any types of accidents like that.
Thank you, everyone, for your questions. Let's thank the speaker again.